So, guys, we have introduced the structural components, the core structural components, of your the computing system, and even the behavioral details, right? How it works, of course, at a very high level, the processor being the master, the memory being the slave, right? So let's continue from where we left. So this is more or less the same thing, but a bit more enlarged now. And for sure, by now you appreciate those CPU registers that we introduced last week, the PC, MAR, IR, MB, and so on and so forth. Of course, they will differ even in name, okay? They will differ processor by processor, okay? And depending on the instruction set of that processor or the ISA of that processor. But this is high level enough for you to appreciate how all processors actually work and how they are structured. So you have your CPU here, having the registers and the execution unit, being your arithmetic and logic units that we have introduced, and the system bus, which interfaces the processor with memory and locations available in memory with addresses and capacity for memory, and how we store, depending on the architecture, also how we store instructions and data, or have separate memory for instruction and data. We will see how that affects performance. As in the decision to either have programs and instructions, like instructions and data stored in one memory, as opposed to having a separate memory for instructions and then a separate one for data. Then we have the I/O module here, which could be your keyboard, could be your display, could be your VR headsets, okay? And one key component there, or one key concept that we need to start appreciating early, is this concept of buffers within your I/O devices, okay? So that's like a temporary storage within an I/O module that is used for the module to communicate with the processor, or even to access stuff from memory, okay? For example, if it is your keyboard or your touch screen, by you typing stuff, okay? Of course, it has its own controller, okay, which controls its operation to be in sync with the processor. But as you type characters, okay, then the device has buffers, okay, where temporarily the data that you are capturing is stored, okay, before it can be shipped to a memory for processing by the CPU. So the concept of buffers within your I/O devices is one that we want to begin appreciating early. Fine. Processor, you can read the slides. Yeah? Yes, it's just a summary of what we've been talking about. Repetition. Okay. It's processing, data, and data generally can refer to both instructions and data, operates. Okay. Yes. So that's what the processor does. And the processing happens within the ALU, being the key execution engine of your processor. Structurally, it has a data path, it is a control unit, okay? Then within your data path, that's where we have the buses, that's where we have the execution units, okay? Yes, we have the ALU, the multiplexers, and other smaller units that make the whole to work with. So there's the description of the data path there. Then there's the description of the control unit, the computer within the computer, right? The computer within the computer. So another summary: CPU registers for fast storage. Okay? Yes, that's where we, we pull things from. Firstly, we pull things from storage, okay, which is much slower. We pull them into memory, right, which is a bit faster than storage. Then from memory, then we start pulling them and putting them into the registers whose performance is closer to that of the CPU. Then we can use them as operands, perform calculations, create results, store them in registers. From registers, take them to memory, and also to storage or even to the outside world. Control unit, there you go. Sing it, understand it, love it, right? Yes, and live it, right? Yes, and you won't simply be a good, data center scientist, right? Or a good computer engineer, okay? But you'll be a good person, which is what the world wants, and that will give you good stuff in life, okay? Because the world wants good people, okay? Yeah, that's it. Okay, yeah, people who are patient, people who have integrity, okay, who know what to do, when to do it, those people, and it's worse when you have technology and then you don't have, all right, those other things. So control, sharpen it, okay, sharpen it, cultivate it, okay, read, okay, read, learn from other people, okay, have good role models and follow, okay, okay. We are tired of having to meet you somewhere in the street and say, hey man, you shouldn't buy times, man. Okay. We're tired. Okay. Yeah. Right. We don't want that for you. But it's in your hands, eh? Yeah. It's in your hands. You are the one on the steering wheel, eh? Yeah. It's up to you. We don't care, eh? Do what you want to do. No, we care. Okay, we want the best for you, right? Do. Okay, so that's the processor. Repetition, okay? Yes. Instruction cycle, instruction format, okay? The clock, okay, which drives everything, and how the length of the clock determines the speed of the processor. So you're fine, all right? In detail, get it, you read, But we are basically saying a control unit works like a finite state machine, okay? Yes, it works like a finite state machine. It has states, and based on the stimuli, okay, it can move from state to state, right? It can be in the fetch stage, depending on the stimuli, it will move to, decode, from decode, execute, okay? And then after execute, it will go back to fetch, right? So it is a finite state machine, just as a 10 style is. So that's a state diagram, state table, the stuff, this one is also like a micro instructions that explain how we do fetch, again, repetition, okay? How we do fetching, all right? So, for example, CPU places address of the next instruction on the bus, okay, on the address bus. So it will copy the value of the memory address register and put it on the address bus, okay? And the address bus is also connected, between the CPU and the memory, right? Yes. And then it sends a control signal, okay? Control signal. So we are already starting to introduce the key components of a bus, okay? Bus, that there are address lines, okay, included in a bus, okay? There are control lines, and then there are data lines, okay? More. Yes, address, control, what? Data, right? Yes. So address lines, that's where we write addresses, either where we want to read, where we want to read, okay? Control lines, that's where we state the task we want to perform. Okay? Are you reading? Are you writing? Okay. So that's the interface that the processor and memory and even other modules found within your computer, how they interact. Okay. Yes. So the CPU will generate a read control signal. Okay. So yeah, I mean, the CPU writes the read control signal on the control lines, and then that will be read or heard by memory, okay? Then it's, okay, the CPU wants me to read from this address on the address line, okay? Then it will do a read operation and write the result on the data lines, okay? The data lines. And the CPU will do what? Will take data from the data lines, store it into in the either current instruction register or memory data register. So you get the process. And this is an example, complete high-level finite state machine for a MIPS processor that we will be focusing largely on. It summarizes what we have been talking about, right? Fetch, decode, execute, write back, go back, okay? And how the processor shifts between those stages depending on the inputs, okay? Depending on the inputs. So how do you implement the control unit? There's either microprogramming or hardwiring. Okay. Yes. How is it implemented? It's either microprogramming or hardwiring. Microprogramming, you write a program, for example, that does this. Okay, you see this? Okay, or this, okay? A program that implements the finite state machine that defines how the CPU works, okay? That's micro programming, meaning it's a program that drives the computer, right? So that the computer can run programs, okay? So the function of the control unit, meaning when you are in this state, okay, when you get this input, go to this state, it's written as a program, okay? It's written as a program. And, you know, that's option one, or hardwiring, okay? So you convert the function of the program into a circuit, which is fixed, okay? And it will do exactly that. So you have those two options. But the one which is mostly used is micro programming, okay? Yes, it's easier, you know, and it's cheaper, okay? The only thing that you want to do as the vendor of the processor is to make sure that no one has access to the microprogram, or it cannot be changed, right? Okay, because what makes an Intel Core i3, okay, is the control unit, okay, that implements that Core i3 functionality, right? So if that is implemented as a microprogram, right, that should stay, I mean, it should be deployed in such a way that it cannot be tampered with, okay? Yes. Hence why, I mean, it's written, you know, to ROM, okay? ROM, read-only memory, okay? So it's instructions that are there, but they can only be read and cannot be written. So that's, and this is how they differ, okay? This is hardwiring. You create this circuit which is hardwired to implement the logic of your control unit, you know, the finite state machine, or you have micro programming, where you have storage for storing that micro program, and it's a read only, okay? Then the processor works by reading from storage, okay, and executing those micro instructions to supervise the operation of the entire processor, okay? So here's an exercise for you that you can do, right, without a problem, at your own spare time, drinking tea, coffee, right? Yes. It's just an exercise that repeats what we are talking about, but now at a near practical level, okay? You have memory with addresses, okay? 300, 01, 02, and then there are instructions stored in each location, and then there are CPU registers, PC, accumulator, and IR, okay? Then you have opcodes here, okay? Opcodes. And already by looking at the opcodes and by looking at the instructions stored in memory, you can tell how big the opcode bits are, right? Okay, there are 4, right? Yes. And then you can tell how big the instruction word is. Okay? Give a guy. Huh? How big is the instruction word? 4. 40. Why do you think it's 40? 2020. Oh, perfect. Yes, yes, yes. That was 40 for that processor. Okay. Yes. But we wanted to consider this one. Okay. So I'm saying, for example, by looking at the memory words. Okay. How big? 16 bits. Okay. Yes, because you have 1940 as a word in memory. Okay. And it's in hexadecimal. Okay. Yes, which is 4444. Okay. So it's 16 bits. Okay. So what happens? PC is pointing at 300. Okay. Right. So it means we need to fetch an instruction from address 300, which happens to be 1940. Okay. We fetch it and then we put it inside the instruction register, which is here, IR. Okay. Meaning we take 1940, we put it in what? IR. Okay. Step 2, we need to decode that instruction, which is inside what? IR. Okay. How? By looking at the first 4 bits. Okay. Which is 1. Okay. It's 1, meaning 0001. All right. And it says it's a load instruction. Okay. Load instruction. So load a value from memory and store it where? Inside the accumulator. All right. Which means the 1 is the opcode. All right. The remaining 12 bits are the address bits. Okay. So 940 is the address where we need to read from memory. Okay. Hence why in step 2, having decoded that this is a load accumulator from memory, where from 940 we go to 940, right? We load 0003, we load it into the accumulator, right? Then we are done with that instruction. We go to 301. You can do the process. Yes. Fine. So one other concept that that we need to appreciate early on is the concept of interrupts. Okay. Interrupts, which means the instruction cycle is not, in practice, the instruction cycle is not actually perfect as it is here, right? Where it's fetch, decode, execute, write back, fetch, it's just nice, right? Yes. There are lots of interruptions that happen. Okay. And interrupts are a mechanism that are used by a processor. Okay. To handle other operations, okay, that may be required while it is busy doing something serious. Okay. All right. More. So purpose of interrupts allow other modules to interrupt normal CPU processing. Okay. So your phone is working, right? And then you do what? You plug in your headsets. Okay. Right. It's working. Okay. running Android, WhatsApp, blah, blah. Okay, it's working. The processor is working, okay? Then you plug in what? Your headset, all right? Okay. The processor cannot just continue doing what it is doing, all right? And ignore the fact that something just happened, okay? All right? So interrupts are used to manage things like that. When the headsets are plugged in, right, the audio controller will create an interrupt, meaning it will interrupt the processor, okay, meaning it sends a control signal, okay, to the processor. Then, oh, okay, who is interrupting me? Okay, it's an audio controller. All right, fine. What do I do? All right, right. What does he want? Then it pauses what it is doing. It executes that code. It finishes. Meaning, I mean, for example, it connects the device. Okay, and if it needs to issue a notification, right, to say, oh, then a UI notification, all right? It issues that, do you want to connect this? Okay, you want to use this? User says, yes, I'm fine. Then it can go back to what it was doing, right? Yes. So to allow other modules to interrupt normal CPU processing and to improve efficiency by avoiding CPU idle time during slow operations like what IO. So we will see at times you are copying a file from disk, okay? I mean, from what? From an SD card, okay, into your phone storage, okay? You're copying files, okay? And of course, reading from storage is costly, right? Okay. And we don't want the processor to wait for the IO operation to be completed, okay? For it to, to continue doing what it was doing, all right? Yes, so when the IO operation starts, the CPU can be interrupted. It says, okay, who needs help? Okay, it's the SD card. What's happening? The user wants to transfer data from the SD card into internal storage. Okay, fine. Then it runs code to initiate that. Once the IO process has been started, then it can leave, okay, and continue what it was doing, because it doesn't need the processor to transfer stuff from SD card to internal storage, okay? The tool can do the transfer, right? While the processor is busy doing other operations, okay? But when the transfer is complete, the processor has to be interrupted, right? Yes. Okay. So that if there there's feedback to be sent to the user, okay, you can say done, okay, yes. So in that way, interrupt helps to improve efficiency of operation of the CPU to avoid that unnecessary idle time, okay? Where we say, okay, it's transfer, fine, we wait, all right? And then the CPU can only continue after the IO operation is done. How interrupts work, you understand it now, okay? So there's the pausing, and then depending on who is interrupting, okay? It means the processor should have interrupt handlers, okay? Which is software, okay? If it's a mouse, I run this code. It's a printer, I run this code. Okay, it's okay. I run this code. Each IO device has its own interrupt service routine, okay? I mean, that code which has to be fired when that particular device actually interrupts the processor. And that's what you do when you write device drivers, okay? Because I mean, if you have a new device which you want to work with perhaps Windows or Linux, okay? It means you need to tell Linux, okay, what it should tell the processor to do when that device is plugged in, okay? Meaning you write that code, okay, I plug it, okay, run this code, do this, okay, do this. Hence why if it's a printer, at times you have to install software, okay, for that printer to work on in Windows or in Linux, okay? That software is device drivers, which is what? Interrupt handling routines, okay? That will be executed by the operating system to do what the vendor of that device wants to happen when the device, is in operation. Interrupt example, okay, key steps in interrupt cycle. Yeah, processor detects an interrupt signal. It suspends the current, program execution, and of course, it needs to save the state. Executes the interrupt handler, right, and then goes back to what it was doing. Okay, benefits, you see them. So this diagram summarizes that, okay, since your eyes are good, okay, you can look at it, all right? Look at it at your own spare time and understand it, all right? But basically, this is processing without interrupts. This is processing with interrupts, okay? Showing how you have a user program here, okay? And then inside the program, perhaps you want to do a write operation, or read operation, and without interrupts, transfer will have to go completely, to the IO module and run everything and wait for the IO operation to be completed, right? But with interrupts, we can pause, run the routine, continue while the IO operation is being done. Okay. So hence why we said the instruction cycle is not as perfect as we had drawn it, all right, in practice. Okay. There are these interrupts which are it's Bluetooth, it's Wi-Fi, okay, it's busy, okay. Every IO is attempting to interrupt the processor. So start, fetch, execute. If there are no interrupts, okay, you just continue. But if there is an interrupt, then instead of running, if after you executed instruction 300, okay, when there is an interrupt, it means the next instruction is no longer at 301, okay? It could be at 501 somewhere, right? Depending on where that routine that drives that device is stored, meaning the processor will have a map, okay? Or for printer, this is the beginning of the, interrupt saving routine, okay? For mouse, for VR headsets, this is where we go. Memory, we spoke about memory into your file. Okay? Fine. You have primary one, which is your RAM. Then you have secondary one, which is your hard disk. okay, or your flash drive, okay, or your flash storage on your phone, or on your smart fridge, or whatever, smart TV, okay? Yes. Then types, it can either be volatile or it can be what? Non-volatile. Volatile means we power it off, it loses everything. Okay? Yes. Non-volatile, it retains data even when it is not powered. And then there's this very important concept that we will build on later when we do a unit on memory, the concept of virtual memory, okay? Which is used to give the user the illusion that they have big RAM, okay? You wonder how you have a phone in perhaps 4 gigs, okay, of RAM, but you are able to run so many applications on the phone all at once, okay? Android, okay, what else? WhatsApp, Netflix, okay, whatever, okay? And applications run from RAM, okay? When you install them, they are stored on flash, okay? But for them to run, they are loaded from flash into memory, all right? Yes. So through virtual memory, the processor fools you or fools, it fools you, the end user, into thinking that we have maybe 16 gigs of what? Of RAM. How? By shuttling things between RAM and storage, depending on need. Okay, right? Yes. Of course, we will discuss virtual memory in detail, but that's the idea. Okay, and also the processor uses cache memory. Cache memory. To put itself, okay, into thinking that it has a big pool of registers, okay, okay, um, you know, or a big pool of main memory, right? Yes. How? You have the CPU, right? And then there are registers. Then there's the cache between registers and what? And main memory, right? And then after main one, you have the storage, okay? So the same way that virtual memory fools the end user into thinking that you have what? Unlimited what? Unlimited physical memory, okay? Cache also transfers or catches things that are frequently used, okay, and keeps them closer to the processor, okay, so that there is an illusion of unlimited registers, okay, basically. So we will see the concept of cache later when we discuss memory in detail, all right? But it's that faster temporary storage for main memory, so that instructions or data that is often accessed in RAM, okay, it's pushed. I mean, it's stored temporarily where? In cache, okay? Yes, because accessing it from cache is faster than going back to RAM, okay? Yes. So the CPU looks for it inside the registers, okay? It's not there. It doesn't want to go all the way to to RAM. Okay. Yeah. So if it is frequently used, it is stored in the cache. Okay. Yes. And then of course to pull it from the cache into the register is P. But at times it looks for it in the register, it's not there, it's a miss. Okay. It goes to a cache, it's not there, it's a miss. Okay. It goes to RAM, it's not there, it's a miss. Okay. Then it has to put it from storage. Okay. Take it into memory, then into cache, then into register. Okay. Yeah. So you have virtual memory and cache to try and minimize going all the way. Okay. Many times because that will affect the performance of your computing system. So this is the memory hierarchy, which is used to give an illusion of unlimited memory. So performance, no man, you're fine. Okay. Yeah. We have said memory has to try and match the speed of the processor, okay? Because if not, it becomes the bottleneck. Okay. Yes. So size, kilobyte, megabyte, I mean, what? Um, this is an example detail for example, the Core i7 processor detail showing the architecture. It's 64 bits. It has 8 CPUs. Okay, 4 cores per socket. Okay, for example, it has level 1 D cache. Okay, meaning level 1 data cache. Okay, of size what? 32 kilobytes. See that? So you will have RAM of 4 gigs. The cache is like 32 or 16. Then you have around 64 registers. Why? The faster they become, the more expensive they are, and therefore the fewer they are. Okay, the higher you go. All right. And then of course you can see that the CPU is clocked at 1.2 gigahertz max, 3.4 minimum, 1.2. All right. I/O, we spoke about it. Input, output, dual, fine. Okay. Siri, VR headsets. Okay. Yes. 3D printers. 3D printers where actually now there are cars that are 3D printed. Again, you just print a car. And you have this machine that prints a car with wheels, and the engines. Okay. Yes. And now the efforts to now print organs. No, okay. I'm serious, okay? Yeah, I'm serious. I mean, there's research and work to print human organs. Print them. Print the organ. Yeah, so all right. So I/O, you understand it, LCD, how it works. You can read the slides or buses. We spoke about buses, okay? Spoke about buses, control lines in the bus, data bar, address. Ow, good. A deal.